Okay, let's get started. This room was available. It's just nicer room than WS14. तो वहाँ पे मेरा computer भी नहीं चलता है, so I thought I'll just do it here. Hope I guess everyone got the message. So last time we did some more demos, and towards the end, I had sort of given you a simple example of how one could build a power divider. But we, of course, saw that that had some limitations. So today we will look at this chapter 7, which is about power dividers and directional couplers. And I had mentioned to you that these are 3-port and 4-port devices, which allow you either symmetric power splitting or asymmetric power splitting. They work on different, slightly different principles. And the chapter has many different kinds of designs for all of these, but we will not go through all of them. We'll just do some of the basic ones to get an idea of how these systems are actually analyzed. Again, as I said, today, because of access to powerful computers and softwares, you don't really need to go through the analytics to understand these things, but going through them for some examples gives you an intuition for how to think about devices, something if you might make your own devices in the future. So that's sort of the goal of this discussion. So here some basic properties are mentioned, and we sort of already have discussed this, that you can have a power divider which by definition has one input port and 2 or more output ports if you're talking about more than 2 division, but we will stick the conversation to just 2 outputs. There could be a 4th output even in that case, depending on how the device is actually constructed, right? So in general, the idea is that you send in some power P1, and on the output, you can get some fraction of that power on one of the ports and the rest of the power on the other port. That's the ideal configuration. And the simplest version of this is the equal power splitting, where you get both powers at the output. The same device operated in reverse, if you use the output ports as your input ports, then it's supposed to combine the power. And we've already seen in the demonstrations what happens when you do that. So there are some caveats on how to use these power dividers in reverse when your application is for combining the power. And here, I just want to make a point that this is actually very different than what you can do again in low frequency electronics, right? So you have all probably built the op-amp summer, which is a very simple device, and it just gives you the sum. There is no consideration about power loss and things like that. It doesn't even matter on what the different signals are. But for passive microwave devices, and remember the op-amp is an active device, right? So there could be a passive version of a voltage combiner at low frequencies, which might follow similar principles. But again, here we are going to be thinking in terms of waves for at least some of the aspects. So this power combining operation is in general not an ideal operation in all cases. We will come to that later on, but I've already mentioned this to you in the context of the demos that if the signals are in phase, then they will come out of the what was the input port earlier without any power loss. But if they are in general 2 independent signals, then you will not get lossless combination of 2 signals. And I also define these terms to you for you: isolation, coupling, and directivity. These are at least in the power divider, there's no concept of directivity that comes in when you go to the 4-port directional coupler. But isolation and coupling are important quantities. So there's also matching, I guess one should keep it here. But in general, we assume that we like all devices we are working with to be matched to 50 ohms on all the ports. So we will see that if you are restricted to use 3 ports or 4 ports, then how the general properties of S matrix and the constraints you have about reciprocity in a passive network, or if you want things to be lossless, that you actually run into some constraints on what can and cannot be achieved using such networks. So these 3-port networks are also sometimes called T-junctions, because if you remember the example I gave you on during the last class, we had put in some transmission line and we split it into 2 transmission lines. I mean, a generic way of drawing this would be something like this. And that's one of the reasons why it's called T-junction. It also resembles an actual device when it's constructed using waveguides. So these are not the transmission lines we have been discussing. These are now waveguides where you can again have wave propagation by using like solid rectangular tubes and things like that. Those are often used at very high frequencies, usually above 10-20 gigahertz, but you can use them even at the usual frequencies of 1 to 10 gigahertz as well. But they tend to be very bulky because, again, the sizes of those things are related to the wavelength. So the smaller the frequency, the larger the wavelength. So we will not look at waveguide stuff much at all, except for in passing. So the generic S matrix is given here. It will have 9 elements, 9 complex elements. If you say that it's going to be a passive material with no fancy anisotropic material, which means this magnetic stuff which we talked about, then it has to be reciprocal and the scattering matrix has to be symmetric. And then you also want the ports to be matched, and ideally you want the thing to be lossless as well so that you don't have any power dissipation. But what this section discusses is that it's actually impossible to satisfy all of these 3 constraints for a 3-port network, which is a reciprocal network, which is matched at all ports, and it is lossless. Right? That's the ideal power divider you would like. If it's a 3-port system, you don't want any power loss, which means output power is equal to input power. You would like it to be reciprocal because you're constructing it out of maybe standard passive components. And then you, of course, want all of to be matched. So this section basically does the math. I mean, we can sort of quickly see it. It's not very complicated. So they start by this assumption that your ports are matched at all ports, which means the reflection coefficients S11, S22, and S33 are all 0. So here, here, and here. And then they have used the fact that it's symmetric and basically left it in this form where you have essentially 3 unique elements, which are this S12, S13, and S23. And then you go ahead and write down some of the conditions which we had briefly discussed earlier, that it has to satisfy the unitary property if it is lossless. So unitary property essentially translates to power conservation in this context. And if you then write down what that means, you see that it's basically not possible to satisfy all of these conditions. So you can try this at home, but this is basically fairly straightforward to see that you will not be able to find a solution. Basically, if you put one of these things to 0, everything just becomes 0 and you don't get anything to work out. So 3-port network cannot satisfy all these 3 properties: lossless, reciprocity, and matching. So you can start relaxing those conditions one by one, and then you can get some type of devices. Okay, so here they sort of start with the non-reciprocal as the first one, in which case you can now get lossless transmission and matched on all ports. And this is the device we also saw in during the demos. It's a circulator, right? So it turns out that circulator, even though it seems to be doing somewhat of a non-standard operation, the fact that it's non-reciprocal is actually one of the things allowed in a 3-port network most naturally, being lossless. But then you only have power transmission from here to here, but doesn't go in the reverse direction. So it doesn't satisfy reciprocity. And this is what is called circulator. This requires you to use some ferrite material, magnetic materials for how it's standard constructed. Turns out that that's actually not what to say. It's not the only way to do it. There are active circuits, and in fact, this is a very strong field of research in the superconducting device community, is how to build non-reciprocal circuits using superconducting circuits without using this magnetic stuff, because there is a fundamental problem that superconductivity and magnetism don't go well together. If you use these circulators, which are available, there are cryogenic versions of these things available. They have always a permanent magnet attached with them, and that stray magnetic field can actually affect your experiments. They tend to be bulky. So there was a requirement for doing these kind of operations even on chip, like integrated with the devices you are actually making. And the primary purposes of this kind of non-reciprocal thing is two things. One, I showed you the reflection measurement, so for routing signals from in to out. And the second is actually for protecting your device from noise coming from further down the chain. So you want the signal to go this way, but there is some noise coming this way, which you would not like to reach your device. So these are the two main purposes for which they are used in these cryogenic experiments. And these circulators, even though they do the job, they are bulky and they can have losses, a little bit of loss as well, which sometimes can be an issue. So it turns out that if you use nonlinear systems and you drive them with the microwave energy, you can achieve these kind of operations. So there was a whole slew of experiments done in the last 10 years which have shown this. None of them are commercially available as a product yet, because it still requires, it's quite complicated to get them to work. So the circulator itself becomes an experiment. And though ideally you would like it to be just a part of the rest of your experiment. So it's actually an active area of research. So it's moving on. You can then, so here they basically discuss the fact that if you are able to remove the non-reciprocity condition, then you can get perfect transmission in one direction and no transmission in the other direction. So ideally, it's possible. So there's no fundamental limitation that there has to be some loss. So in fact, it says that the most ideal operation is perfect transmission in one direction and no transmission in the other direction. In practice, you will have this something like 0.1, and this has something like 0.9. For a real practical device, and maybe even some insertion loss as well. So the other possibility now is that we can try to relax the matching part. So in this case, they say that it can be realized if only two of its ports are matched. Okay. So remember that the strictest condition we were talking about, where we put this condition for the entire network, reciprocal, lossless, and matching on all ports. So here we are relaxing the matching part on only one of the ports. And yeah, so you again start with this one. You leave this guy now non-zero. Unlike before, this was also 0. But this actually leads to a fairly useless kind of a device, which is this. It's basically not really a 3-port device. It's a 2-port device and a 1-port device, which are just separate. So what you get after putting these conditions in here and allowing the port S3 to be mismatched, the only reasonable solution which comes out is that the network separates into two components. One is a matched 2-port line. So if you look here, this is just a transmission line, 50 ohm transmission line, which is matched. So, and it's bidirectional. And then the third port is actually not doing anything. It's just a separate port. So it's not really a realistic 3-port device in that sense, but that's what the equations give you, that one can do if you try to demand this this kind of a behavior. Okay. So this is again an example that just satisfying the mathematical properties need not always necessarily lead to a device which is useful. And then the final case is if you have reciprocal matched at all ports, but now you allow the network to be lossy. This is the case of the resistive divider. We had seen this again in the demos last time. So this was the 6 dB splitter where you ended up losing 50% of the power you send in, and it actually dissipates in the internal networks. In just a little bit, we will actually see one way of building this resistive divider. Okay. So you can, I recommend you go through this math just to convince yourself. You can also play around with this in microwave office to see what you get if you try to put those kind of constraints. When you go to now 4 ports, there are more possibilities. Now there are many more elements. Again, you would like to start with these 2 basic ideas that you have matched ports, right? So all the SIIs are 0, and you have the reciprocal requirement put in. And then you can again do the same kind of analysis, and now you get many more options. So we will come back to this 4-port stuff later on, but they can essentially be divided into some certain classes of devices, which are basically these directional couplers. Okay. So we'll come back to that later on once we get to the 4-port case. So we will move on with some 3-port examples. Okay. Any questions so far? Okay, so this T-port T-junction divider allows you to build a lossless divider, but we'll see which of those properties one has to sacrifice on. Okay, and this is these pictures here show you in A and B are the waveguide versions of that, so we don't have to worry about it. But here, in C, you have this microstrip version, right? So we looked at this briefly in the last class, not in the microstrip form, but this is how you could build one. You have an incoming microstrip, and then it just splits into 2, right? So this works because the ground plane is common underneath. So you now have 2 transmission lines coming from 1 transmission line. And do you remember we had discussed how, in which property this would fail? Matching from the output side, right? So we had said that if you want this to be 50 ohms, we could put 200 ohms here, and then you don't have any reflection when you're going in this direction. But now if you come from this direction, then the 100 ohm line sees a 50 and 100 in parallel, so it's no longer matched in this case. So here, I think I had mentioned this as well, that if you choose the output line impedances, you can also get unequal split, right? And it also talks about using quarter wave transformers if you want to go from 50 to 100 and then back to 50. So you can at least keep everything in the 50 ohm 50 ohm characteristic impedance. And only if the output lines are matched, the input looks matched, right? So you have to terminate the output lines with matched ports. Only then the input will not see any reflection at the splitting point. So, and of course, there is no isolation between the 2 output ports. And this is, it's not fundamental to the 3 properties we discussed, but isolation is a useful property in practice for a device, because you don't want signals on different lines to necessarily talk to each other. So here the problem is that a signal which comes from here could go to the other output port. So you'd ideally like the output ports to be isolated with each other so that there's no power going in, but that will not be satisfied in this particular case. So we already saw that last time. So now let's look at this one in a little bit more detail. Okay. So this is a construction of the resistive divider. Now this figure can be slightly confusing. So let's see what actually, I'm going to redraw this in sort of a transmission line form, this coax picture. So the center conductor has a resistor now. Okay. That's this part of the circuit. Okay. And then they have just drawn this other one. So if you sort of look at what's happening here, this is just the second conductor, and that's just going along in all these three directions. So that's just this part of the circuit. Okay. So it's easier to maybe visualize it like this one. And then these grounds are all common. Okay. So if you think about it, it's really just, this is the circuit. The rest is just the 50 ohm lines feeding into the system. So if you had to write this, let's say from the perspective of, say if this is port 1, 2, and 3, and I now draw the port 1 as a voltage source with 50 ohm source impedance, then this has an extra resistor going here. And if I terminate all of the other ones also with 50 ohms, then, so this is, let's call this small r. This is small r, and then that would be 50 ohms. And there'll be another one here, r. This will be also 50 ohms. You can connect these. This is all ground. So now it sort of looks like our conventional voltage divider, but of course there are some extra resistors. But this is all in order to maintain the matching of the overall system. So how does that actually come about, right? So that's the calculation you do here. What you want, maybe I should erase this here. If you look at it at this plane, what I have done right now is I've terminated. So remember, this is port 1, this is port 2, and this is port 3. So I've terminated port 2 and port 3 with 50 ohms. So that's the matching condition. And the input source is, of course, 50 ohms. So what we want to know is that from this point, does the rest of the circuit look 50 ohms or not, right? If it does, that the value of R we need, which gives you that thing, will basically be the matching condition. Otherwise, this circuit is completely symmetric, right? There is no difference between any of the three ports here. They look exactly identical. Yeah, sorry. So what it also means that in this case, there is really no difference between input and output. Any port can be input and any port can be output. So what we have here is these two branches here and here, they are in parallel, right? So that means the resistance from this point to ground is going to be 50 plus R over 2. And then this little r here is in series. So that's the total resistance. So in this case, because there are only lumped element circuits involved, the DC analysis and the AC analysis is exactly the same. Right? There is no capacitance, no transmission line, nothing to worry about, because we have only chosen this particular junction as the device. So this needs to be equal to 50. So let's see if I did this right. So this would mean 3R02. So that means, so yeah, 550 is 100, then minus 50, so 50 over. Right. So this is basically what they have chosen here.
This Z0 is like a effective Z0?
Sorry. So, okay, I think I've confused you a little bit because of the nomenclature. They already started in this figure, which is there in the book. They already started with the solution, and then they show you that that solution is the correct solution. I've chosen a general value of R, small r. So R is Z0 over 3. That is basically what I have found. Z0 is 50 ohms. They are just saying that this is true for any generic characteristic impedance as well.
I have something at the end of the transmission. When I'm looking at Z0, I'm looking at like an effective Z0. I consider everything at P1.
There is nothing else.
No, let's say if I have something.
No. See, if you have something, then for that specific case, you can compute what the input impedance can be using the scattering matrix of the power divider, this one, and then applying the boundary conditions accordingly. What we are trying to find out is, what does a circuit which is drawn here like do? I mean, we started with the idea that this is a power divider, and it's a lossy power divider because I've used actually resistors in its construction, and those resistors are going to dissipate energy, which means it's not going to conserve power in terms of just the ports, what comes in and out of the port. So in order to construct that device properly so that it performs the operation I'm doing, I'm now going through some calculations to figure out what is the correct way to do it. So the first condition I have assumed is that I want everything to look matched. So when you say that there might be something there, that something is this thing here. I've chosen that port to be terminated with 50 ohms. It doesn't matter if it is in reality, whether it's a 50 ohm transmission line, which is then terminated by a 50 ohms, or as we discussed in many classes ago, it could be an infinite transmission line as well. As long as nothing comes back and it looks like a 50 ohm characteristic impedance, then that is what we are doing. So I'm checking that if I put 50 ohm terminations on two of the ports, and I look at the input impedance from the third port, what value of small r for this divider network would give me 50 ohms? Because that is the only combination which I can use to construct a match system. And then I also made the point that this circuit is completely symmetric on all three ports, so the same analysis would apply for all of them, right? So is this part clear? Yeah.
So when you say that the center conductor has this resistance, it's just at the end. Like we used to have this load, somewhat like that. So, or like you're saying the entire line suddenly has a series which.
It's a series. So it's now a resistor which we're actually physically putting in. So
it's just at the end, right? Or
well, end.
Say it's throughout. Like, we never really discussed about it before. We always say it's in parallel. Whenever we see a transmission line, there are parallel.
Yes, that's right. So far we have only talked about shunt resistors, but this is actually in series.
So I'm asking, is it at the end or it's throughout?
End of what?
End of the transition.
It's a lumped element, so it is at one point. So okay, so the reason I'm slightly confused is that the device is just what is contained in this circle. This circle. So there is no beginning or end here, right? This is the input port here, these points here. Right? These are the port connectors. So you have to think of this blue circle here as the 3-port network. And the circuit is the actual circuit whose 3-port matrix we are trying to calculate and trying to figure out what it will do. This transmission line is just, it's like a dummy thing because that's representing my input lines. But if I now go here, I have even removed this transmission line and basically just directly replaced what would have been a source here, right? This is a 50 ohm source, which is basically this part here. So these R's are at the end of these transmission lines, but inside the circuit divider, you have just these 3 resistors. So these are 3 physical resistors. Maybe where was that T junction thing here, right? Here. Let's actually think about how this would be constructed in practice. And let's say we want to use a microstrip design. So I'm just using this as a reference. I'm going to redraw this. The reason you have to do this is that because in practice, if you're going to use this as a device, you're going to have connectors, right? So there's going to be some connector here, which is going to launch from coax onto let's say a microstrip. So this is going to be a 50 ohm microstrip line. So far, all that has happened is that there could be a long coaxial cable here coming here. That's also 50 ohms. This connector is 50 ohms. This microstrip is 50 ohms. So everything is just one big long transmission line in ideal case. Yeah. No, I'm coming to that. So this is something you have to be careful about. This transmission line is right now, its only purpose is to bring the signal to the actual device. The device has not come, the operating part of the device has not come yet. So that's what's going to come next. I'm going to have a similar system here. Sorry. So again, a connector here, some launch here, a 50 ohm. I should maybe write Z0 equal to 50 ohms. So it's a transmission line with characteristic impedance 50 ohms. And I'm going to do the same thing over here. Okay. Now, at this point, I'm going to put, say, some surface mount component, right? And I have let me draw this again. Oops, sorry.
Just one question, what are you exactly calling the launch?
The what?
Launch, the tag or the small.
This thing is the connector, and then this transition from here to the. We have not studied this part in detail. I'm just saying you have seen those devices I showed you, right? There is a connector at the outside, and then the pin goes inside, and there's a proper way of doing that to ensure that there are no impedance matches here. I'm just saying this is how the actual device is going to look like. Let's not worry about what is happening here. Okay. Oops. In the middle, I'm going to put another patch of metal. So remember that all of these 50 ohm microstrip transmission lines is just a strip of metal on that surface, right? And then what I need some resistors in here now. So it could be a surface mount component mounted like that, which has the value R equal to 50 over 3. And I put another one here, and I put another one here. That's what that circuit means. So I have an incoming section of transmission line. Then I have a 50 ohm, not 50 by 3 ohm resistor. And then I have exactly the same thing in all of them. this length of transmission line is completely irrelevant. Because all the way from here down to wherever this cable is, everything is 50 ohms. So it's just moving some reference plane. The active part of the device is really what is contained here. It's really just 3 resistors of 50 by 3 value, all connected with one point and connected to the center conductor of your transmission line. Right? There is no connection on the ground on this side. The ground is anyway for the microstrip, it's common. So you know, what do you call beginning and end here is a bit vague. So, but what is important to know is that these are the ports. And by adding these extra lines, I've just extended that port out to a connector in the physical real case. So that's all that is happening. Okay. So is this part clear? What the actual device is? So it is in series on the center conductor. It's not a shunt to ground. In any way, in microstrip geometry, it's difficult to make shunts to ground because the ground is underneath. And that's sort of a side point. So if you now go back to this circuit here, for ports 2 and 3, I have terminated that transmission line with a 50 ohm resistor so that we are terminating with a matched port. Because remember that when we used to compute S matrix, you have to make sure the boundary conditions are all correct when you're trying to, right? When somebody says it's matched on port 1, it's assumed for in this case for a 3-port network that port 2 and port 3 have already been terminated with a matched load. Only then the port 1 will be matched, and vice versa, right? For all the same ports. So since I started with an unknown resistor R here, I'm just trying to show you how you compute that R to get the matching condition. So you put the 50 ohm termination here, and then you look at what is the impedance between these 2 points, right? And that is easy. It's 50 plus R and 50 plus R in parallel. So that became 50R over 2. And then plus R. That's the resistance between these 2 points. And that needs to be equal to 50 ohms if it should look matched. So we solved for that, and we got that R is 50 over 3, which is what they had already assumed. So then they go ahead and show that if you assume R is 50 over 3, or in this case, Z0 over 3, so this would work for any characteristic impedance system. If the characteristic impedance is 100 ohms, then the correct resistor is 100 over 3, right? Because the calculation will not change. So once that is done, you know that you have achieved this by symmetry because it's completely symmetric. Then you need to calculate to make sure what is the output you actually get. So far, you have only looked at the impedance aspect of the ports. We have ensured that it will look like 50 ohms. But then if I send some signal in here, what is the signal I'm going to get at port 2 and port 3? Okay. That is this calculation. And here also you can basically use this circuit here to compute what voltage drops you're going to get in at different points, right? So that's again easy. You can add these 2 arms in parallel and then put that, and then you know that the total drop current is going to be this, whatever is voltage here, V divided by 50 plus R plus 50 plus R over 2. That's the total current. And then you can multiply it by 50 plus R to get the voltage drops across each of these arms. And then from that, you can compute what will be the voltage here. So this is what they compute. And you get this point, that if the voltage at port 1 is V1, then the voltage V at the center of the junction is 2/3 of V1, which is basically this point here. And then you can compute that V2 is going to be 1/2 of V1. So remember, the voltage is half. This might look misleading that, oh, it looks like equal power splitting, but it's not. Right? The output voltages V2 and V3 are half of the input voltage, which means the power is 1/4 of that. So you get 50% power loss. But your S matrix looks nice like this. So all zeros on the diagonal for matching. Symmetric, you have ones, and all the S21, S31, S23, S12, S13, S32. Everything is just 1/2. So this is that of the S matrix for a resistive divider. Where the ports are matched, it's not lossless. You have losses, and it's reciprocal. And here it says that the reader may verify that this is not a unitary matrix because it's lossy in this case. Okay, so this actually is a very simple calculation because the methods we used are identical to that we would have used if this was a low frequency circuit as well. Right? I can always convert from voltage to power because there was no wave aspect of it really used. In practice, can you make 3 resistors like that, which are only resistors without any capacitance or inductance at all the frequencies of interest, is what will determine its true performance in the microwave frequency range. This will work like a power divider all the way down to DC. That's why if you remember that box said DC as well. But at higher frequencies, there'll be a cutoff because you cannot make resistors work to arbitrarily large frequencies. So that again depends on the construction, how small it is, what kind of stray capacitances and inductance it has. One needs to worry about that. Okay. So what are we doing on time? Oh, okay. Finish by 5:30. Okay. So we'll now move on to the, yeah. I know. I just said I have to finish by, I looked at it and I thought, oh, I have only 15 minutes left, but it's 4:47. So we're only halfway through the class. I think it will not take more than 40 minutes. If it does, we'll do it in the next class. So this is the circuit I've been mentioning many times, and we have seen it in our demo as well, though we never really verified that what's inside is actually a Wilkinson power divider, but most likely it is. So the point here is that a lossy 3-port network can be made having all ports match with isolation between output ports. So you cannot get the lossless part, but the Wilkinson power divider is lossy. So that's the constraint it's relaxing, but with the catch that it doesn't look lossy in one direction, which is this, that when the output ports are matched. So this is a strange way of putting it. What they mean is if ports 2 and 3 are matched, which anyway we always assume is, then P in, so if this is PO2 and PO3 is equal to P02 plus P03. Anyway, when you're trying to deliver power to the output, you're going to ensure that the output is matched. So this is a strange way of writing it. They say the only reflected power from the output ports is dissipated. Is that if there was any reflection and it was not matched, then the power which is returning will experience loss on its way to back to the input port. But that's sort of, I don't know why it's kind of a strange way of looking at it. But this is what I was even saying in the beginning, that if you send power in the reverse direction, then in general, you will have loss. In some cases, you will not. Okay. So as a splitter, then it looks perfect, right? Because it's lossless, it's also matched, and it's reciprocal. Well, okay, I guess, yeah, it is reciprocal. It's reciprocal, yeah. Yeah, because I'm just pausing because it's reciprocal, but you have to keep in mind that there are other ports involved here, right? So what do I mean by that? So it sounds a bit strange. Let me just explain this. I said it's lossless in one direction, but lossy in the other direction. So how does that seems like it's non-reciprocal, right? But that's because we are not thinking about all the three ports together. When I'm talking about reciprocity, I'm going to only look at a pair of ports. So here, 1 and 2, S12 and S21 will always be the same, right? But if I and similarly, S13 and S31 are the same. But that doesn't mean that if I put power in port 2, the power coming out of port 1 and port 3 will equal to the sum. The sum of that will be equal to the power you put in. So that lossless part goes away. The reciprocity part is only connected with the pairs of ports. It's sort of a subtle point, not really that important, but I just caught myself saying that it's lossless in one direction and lossless in the other direction. But that's because you have to think of the two ports separately when you're talking about the reciprocity. But for the loss case, you have to look at all three ports because we're talking about power conservation, right? Okay. So this here is the actual circuit. So on the left is shown sort of how it would be done in a microstrip geometry. So you have a feed line. So this is where, if I had extended this, I would have had my connector here and some kind of launch coming in, connecting it. Get rid of that. You're only worried about. So feed line is 50 ohms in all three ports, right? And then it does this T-junction kind of splitting. But there are two interesting things going on. First, the split is happening to a different characteristic impedance of transmission line. So these two are √2 of Z0. And they are also quarter wavelength in dimension. And then in addition, there is this extra resistor which is bridging these 2 points. So this point here is basically the junction between the √2 Z0 transmission line and the Z0 extensions on the other side here. When I was talking about the hidden fourth port, this is what I meant. This 2 Z0 resistor, which is internal to the thing, is like the hidden fourth port. Why do I call it a port? Or why am I equating it to a port? Yes, but essentially a port is where power can be delivered, right? A port is actually a dissipative. It's basically 50 ohms for a 50 ohm system. This is not a 50 ohm port, but it's a resistor. So I could, in principle, have, it's tricky to make it, but I could have made a 2 Z0 transmission line and taken it out through the third dimension. That would be a transmission line which connects, basically has the two terminals on either side of these things. And then I could terminate it with a 2 Z0 termination. So it's not a 50 ohm port, but it's a hidden fourth port. This fourth port of this type shows up in one of the other power dividers, which I think I mentioned during the demos. there's something called a hybrid splitter and also a rat race based splitter, which both provide 90 degrees splitting in the phase and 180-degree splitting in the phase. They have this port explicitly there, and it's a port of the same impedance. But essentially, the point is that this device has a resistive element in the construction of the circuit. And that's the reason why it's lossy. But because of the symmetry, that loss only shows up under certain conditions. Right? So we will see that. The sort of the stick figure type of transmission line version is shown here. So let me just walk you through that once again. Remember that these are the two arms of the transmission line, which represent signal and ground, for example, or if it's a parallel, if it's a symmetric thing, it just refers the two lines. So I've just put it in different colors here so that it's clear. Then the transmission line splits into two arms, which is this, arm here and this arm here, and that's basically this part, right? And this original one was this part. The blue also is just, it's just ground, so there is really no notion of that having a characteristic impedance. What it means really is that the characteristic impedance between these two lines is 2Z0, right? That's what. So these two together form a transmission line, and then these two together form a transmission line, right? This one and this one. So the ground is just being propagated. In the microstrip version, that's just common ground everywhere. And then you see that this resistor here is connected between this point and this point, which is basically where the transmission line is changing back to being 50 ohms, which is Z0, right? Again, on the center pin. So we have assumed this to be the signal, and this, let's say this to be ground. So it's between the two signal ports on this side and this side, which is the same as this guy here. Okay. Is this clear? Let me draw here in our familiar coaxial version. So this is Z0. I'm going to use colors for this is root 2 Z0. Then I go back to $50 ohms for Z0. And between these two, I've connected this to Z0. Okay. All three are representing exactly the same information. So here again, the values for the quarter wave section and this extra resistor is already given. We have not sort of derived it from some condition. So we'll just go and see what such a circuit actually achieves and see that it matches our requirements in terms of the power divider. Okay. So one other reason for looking at this analysis is it introduces this technique of even odd mode analysis, which is quite useful in general to handle complicated circuits, because you can simplify them under some special symmetry conditions. Okay. I think we briefly encountered this in some other example. I'm sort of have this vague recollection, but I can't remember now. But it's for this slot line. No. When we are discussing coupled microstrip lines, right? So when you have two voltages, V1 and V2, you can also represent them equivalently as V1 plus V2 and V1 minus V2, right? So this often comes in the concept of normal modes. And you know that when you go into the normal mode picture, some of the dynamics, the motion becomes simpler because the normal modes represent particular symmetries where the system can be broken up into very distinct forms of responses. It's exactly the same idea here as well. By going into this even and odd mode, you are taking one general scenario, turning it into a different general scenario. However, the pieces of that second picture allows you to simplify the overall circuit and compute the response. So again, if you draw this in microwave office, it will compute this instantaneously. But if you wanted to understand this from the perspective of the circuit itself and transmission line equations, this is how you do it. Okay. So this is now a third representation of the same circuit where some changes have been made. So I will explain what that is. You can sort of forget all of this part, okay? Because this is just representing the ground line for the entire circuit. We already saw that in this picture also, the ground is just common everywhere. It's not really serving any purpose, except to say that it's a transmission line with two conductors. So the entire 3-port device has been restricted to only the necessary part here. And this connects with what I had explained for the resistive divider when Panya was asking about starting and stopping. What do I mean by the necessary parts? Let me go back here. These 50 ohm feed lines really serve no purpose in the active performance or the functioning of this device. They are just allowing us to send the signal to a 50 ohm port, right? Because when we analyze this system, we always put some matched resistors anyway, and that's equivalent to, you can put the match resistor here, or you can put it right at this point, and it's the same. So remember, 50 ohm resistor with a 50 ohm transmission line is basically a 50 ohm resistor at that point as well. So that's what I mean by the relevant part. So the relevant part really is just this much, right? It has two transmission lines going in this sort of split format with a characteristic impedance 2Z0 and a resistor connected across the two terminals. Everything which comes on either side is a 50 ohm transmission line. Okay. So that's exactly what they have done. So your ports are here. So this is sort of the port location. This one here and this one here. Okay. So you identify the 3 points. So this port on the left side, this one, I'll elaborate and say, but they've just sort of drawn it in an extended fashion. But these three circles are the same. These three circles are the same point. The potential is exactly the same. They just drawn it like this for a specific reason. I'll explain in just a bit. So your lambda by 4 section, two of them, and the characteristic impedance of that has been written as Z. Even though in the previous case, a specific value was given, root 2 Z0, here they have just written it as a value of Z. The characteristic impedance has all been normalized to 1. This is just for simplicity of the calculation so that you're not carrying around 50 and hundreds everywhere. This is just a mathematical trick. So 50 ohms has become 1 in this picture. That's why here, that 1, because remember, this also should have just been one resistor with value 1, right? Because this is the single 50 ohm. They have just written it like this or drawn it like this as two parallel 2 ohm resistors. Why parallel? Because they are both going from this point to ground. So it's just like this. So this is equivalent to 1 ohm. On this side, there is no such requirement. And here they have connected a voltage source and called it VG2 and VG3. And on this side, the voltage is 0, basically because it's just connected to ground. So the analysis in this case, oddly, actually is coming from the other side. We're actually looking at the excitations on the output port and then trying to understand the S matrix. And because it's a reciprocal system, you can get the other one just by symmetry. It makes it easier to analyze it like this. Finally, this extra resistor, this one, the 2Z0 one here, has been relabeled as R and deliberately split into two series resistors of R by 2 with this point here in the middle. Okay. All of this, you can call it drama, is to be able to identify the symmetry of this circuit. Right? Now, if you look at this circuit, you can sort of notice that it's symmetric about this line. Things are Sorry?
The last two resistors, it's connected to ground. One end.
This one?
No, the
This one? This one?
yes.
Sorry, what's the question?
Like the how this relates to the previous.
Oh, all ports have been connected with matched 50 ohm resistors, which is one in this picture, but the one has been split as two 2 ohm resistors in parallel. We are analyzing this circuit with a matched load on all of them. In addition, we are putting an excitation on the two output ports and calling it VG2 and VG3. But these resistors are 50 ohm and this are so because you need all the input and the output ports to be connected with matched terminations or matched sources, right? That's what. So do you guys now see the symmetry that this, looking at it, this point of this looks perfectly mirror image with respect to that particular plane. And it's this symmetry which allows you to realize that if I now, instead of using a general value VG2 and VG3, if instead I use VG2 plus VG3 and VG2 minus VG3, I can see, which is basically equivalent to these two variables. You can create certain kinds of excitations where because of the symmetry, you can simplify things. So for example, if VG2 and VG3 were equal, then because of the symmetry, the voltage at this point and the voltage at this point will be the same for that mode of excitation. Oh, sorry. So the voltage at this point and the voltage at that point, if VG2 and VG3 were the same, these two voltages will also be the same. Which means that there will be no current that can flow through this cross resistor. Why does that simplify things? Because if there is no current here, I can basically disconnect this entire circuit from this dashed line and only analyze one half of it, because it will not depend on the other half. But the net effect is going to be the combination of the two, right? Because this is going to put some voltage on this end, and this path is also going to put some voltage on that end. And those two will just add to each other. Similarly, if VG2 and VG3 were opposite of each other, then the point, this point here, will have zero voltage, right? Because for the same reason, at port 2 and port 3, the voltages will be equal and opposite. And that means that in the middle, because this is again just two equal resistors, the middle point will always be at 0 volts. That again means, so instead of now disconnecting it, I disconnect in a different way. I put a short there. So again, the two circuits become independent. I can analyze them, but with a slightly different boundary condition, that this red point in the previous case was open, and in the second case was a short circuit. Okay. So that again simplifies the entire network, and then you can compute the responses in a simple way, which is what basically is done for the rest of the circuit. Okay. So these are actually the two equivalent pictures, because it's 0 volts. So I should, sorry, maybe I should just not say short circuit. I should say I connect it to ground, because ground means 0 voltage. That's what I meant by. So sorry, short circuit was actually the wrong thing to say. It's short circuit to ground is the correct picture. So this point, because it's always going to be at 0 volt, you can connect it to ground and it will not change anything. And then the moment you connect it to ground, it again splits the entire circuit into two independent circuits. So what do I mean by that is that this picture where, you know, this is sending some current to the other half of the circuit while this point remains at 0 is the same as this picture with the thing terminated to ground with the same amount of current flowing through that point. So I can replace it with the ground. Yeah. Sorry, Anya, question? Okay. Actually, I do too. Huh? Okay. So that's when it actually does. I was also smelled like LPG for a little bit. So maybe they're using Bunsen burners. Could be. So these are the specific things they have used in this analysis. Okay. Why 2V0? It's just a convention. It simplifies things later on. But they use in one case, which we call the even mode excitation. So this is again a general term which comes, which will come in many other microwave circuits as well. So even mode usually means that things are going up and down together. Odd mode means they are going in opposite directions. So even mode is VG2 equal to VG3 equal to 2V0, and odd mode VG2 equal to minus VG3 equal to 2V0. So then they say that the superposition of these two modes effectively produces an excitation of VG2 equals to, because then you can sum these two, right? And you can calculate what VG2 is going to be. So VG2 will be 4 volts, 4V0, and VG3 will be 0. So really what our starting point is really this condition. Right. We have terminated port 1. We have excited port 2 with 4V0, and we have put 0 volts on port 3, which is also equivalent to just saying it's terminated only with 50 ohms. But to analyze this circuit, we have split this into these two equivalent circuits. with VG2 equal to VG3 equal to 2V0, the even mode excitation, and the odd mode excitation with opposite values. And the reason to do that is you can calculate things simply because of the simplifications you can make under such even and odd mode excitations. So that's what is drawn in this circuit, the equivalent circuit A and B for the even mode. So this is even and this is odd. So the equivalent voltage is still both cases 2V0. That resistor 1 ohm remains the same. You have now this dangling resistor where OC here means open circuit. This is the case because there's no current flowing through R by 2. This is written here as an open circuit. And you do the same thing here. It really doesn't matter in this case because these 3 points are sort of the same potential. But because of the symmetry, you can just break it apart and write that as an open circuit as well. Anyway, there's nothing happening here because this is just connected to that particular point. And for this case, you do the opposite. You again have the same source voltage 2V0, but now you have the R by 2 connected to ground and also this part connected to ground. Because for an odd mode excitation, this potential will also be 0 because of the symmetry. You see that because the two sides are always going to have equal and opposite voltages. So when you come back to this common point, they will cancel each other out. One path will give you a positive signal, the other path will give you a negative signal. So when you come back to the port 1, it will become 0. So that's why they have also connected this to a short here. So now this entire circuit looks a lot simpler. What is our goal? Our goal is to see that given some voltage 2V0 here, can I calculate what is the voltage appearing at port 1 on the input side? So you can also notice that this is again useless, right? It doesn't, sorry. This dangling resistor does not participate in this circuit because there's no current. So you can just forget about this R by 2 completely in this picture. So what do you have? If I now look from this side, I have a 50 ohm resistor with a voltage of 2V0 connected to a lambda by 4 section of a transmission line with characteristic impedance Z. So which means I can compute the impedance seen at port 1 looking out that way, right? Because we know how to use the impedance transformer formula. So I'm going to shift because I need to see stuff here, but also have that figure over there. So I'm going to project this from the other side. 1 second.
This lambda by 4 will work on one particular.
Sorry?
Like a quarter
Oh, yeah. So sorry, I forgot to mention, I was going to say that the very fact that we are using a lambda by 4 transformer here means that this entire operation will work perfectly at one frequency.
But we showed a frequency.
Yeah, but it's exactly the same idea. I mean, do you mean frequency range for the demonstration?
Yes.
Yeah, but remember we discussed that an impedance transformer also works over some range with some variation in its properties. So what you have to decide is what is an acceptable variation in property. So you will see how this one behaves outside of the frequency. And there are more sophisticated versions of the Wilkinson divider where this section here in the middle could be composed of many such lambda by 4 sections. Then you can increase the bandwidth of operation. Right. But yes, I forgot to emphasize this fact that by design, we are going to talk about one frequency, which is where this lambda by 4 is the perfect, because that's what we're going to use to calculate the ideal response. The frequency dependent response is more complicated to calculate analytically, because then you have to use the frequency dependent quantities for the lambda by 4 transformer as well, which again, we usually don't look at analytically, though it's possible to compute it.
So in this case, like,
Volume, please.
V1O, where we write, we have shortened it, right?
Yes. So the O refers to odd.
So it's effectively zero then.
Where?
Very shortened it.
At the this point here. Yeah. Yeah. We're going to use that. So V1O is 0. It is written like that because in this case, there will be a V1E that will have some finite value. So this will just become some value, in this case, 0. Okay. So first we look at the even mode case. And we try to compute the impedance looking into port 2. Okay, so this is actually being done slightly differently than what I just said. Let me get the, where is the annotation screen go? Okay, I guess you can see my mouse, right? So we're going to look from port 2 in this direction. So what does it look like? You have this 2 ohm resistor and a quarter wave transformer with value, characteristic impedance Z. So the impedance seen here for this entire circuit is going to look like Z square over 2. So remember, what we will do. So because I'm full screen mode. Sorry, I'm trying to see if I can annotate. Ah, there it is now. Right. Right. So we are looking at from here, and remember the quarter wave transformer equation is that Z of the transformer square is equal to the product of the 2 ports, right? Z1 and Z2. Okay, 1 and 2 here mean different things. So if I look at port 2 here, which is this point here, I'm trying to transform this impedance by this transformer. So this ZT is Z and Z1 is 2. So Z2 is Z square over. Okay, so this is Z in. So this, I'm calling it as the input impedance seen from port 2 for the even mode excitation. And that is equal to Z square over 2. Okay, 2 here because this is 2. This is 2. Not some random factor of 2. Okay. Now, what do we want this to look like? To be matched, right? So if Z was √2, then this Z in impedance would be √2 square. That's 2 over 2, which is 1. And what is 1? 1 is this. So from this point of view, the entire circuit looks like 1 ohm to ground, which is basically the matching condition. Okay. So that's one of the places where you get that this transmission line section in the middle, the quarter wave section, has to have a characteristic impedance of square root of 2, which in reality means square root of 50 ohms, whatever is the characteristic impedance you're working in. Here, the normalized unit, you get Z equal to 2. So you want Z equals square root of 2. Okay. And if that's the case, Z in, we already see is 1, which means the voltage at this point is going to be just half of the voltage here, right? Because it's 1 to ground. So your oh. Okay. So the next part is slightly tricky. So let me make sure I say it correctly. So what we have verified so far, that V2E, which is this value here, okay, V2E, which is the even mode voltage for port 2, is equal to V0. Why V0? Because it's half of 2V0. We are now going to find the same voltage, but now here on this side, which is V1E, because we need to compute the voltage at this point to know the full S matrix. This we do using the transmission line equations. Okay. So we define the point port 1, this point here, as x equal to 0. Okay. And use the transmission line equation that V of x is equal to V plus. I'll tell you what V plus is in just a second. E to the minus j beta x. Yeah. Oh, what are we? Oh, are we reached that point? Ah, okay. All right. Maybe we can pause here and then finish it off in the next time. But essentially, by using the transmission line equation and putting the values on one end, you can compute what V2 is. And that allows you to get one set of the transmission line. So we'll go through the rest of the calculation in the next class.
Why are we doing the calculation of this segment?
So I said that maybe you were in the restroom at that time. The calculation is easier to do this way. And then you use the fact that it's a symmetric network. So this way and that way will give you the same result. No, in the end, so what you will see is that after going through this is not the full calculation, right? I have only done now even mode excitation for one side. Then I do the same thing for the bottom circuit, the odd mode excitation. Then I compute the whole thing. And what I get is that if I put some signal on port 2, how much signal comes at port 1 with port 3 matched, right? That is basically the definition of S12. But S12 has to be equal to S21 because this is a passive reciprocal circuit. So you compute it in the reverse direction because it's easier to split it into this way. And then you use reciprocity to say that, okay, the S matrix is going to be like that. Okay. All right. So let's stop there.
Sir, will you have some answer to this?
There will be one answer, yes.